Okay, welcome to the 22nd class meeting of the Introduction to DSP. We have just taken the second quiz. There will be homework again. It will be assigned probably by tomorrow. And it's due next Thursday, not Tuesday. But still, on Thursday, we do not have our class meeting because of the festival. So we are going to meet next Tuesday. Got it? So if you want, I can delay the homework to next Tuesday. Okay, I will do that. Okay, here is the overview of our course. We are now working around here, including some of these things. And as I emphasized throughout this course, you now realize how important the DFT is. DFT is one of the most powerful tools you learn in the signals and systems or digital signal processing. It's the core of modern digital communications, such as OFDM modulation and demodulation, which is employed by the current Wi-Fi standards and also cellular standards. So your cell phone has not only the Wi-Fi modem, modulator and demodulator, but also the cellular modem. Both perform DFT a lot of times within a fraction, not fraction, probably million times during the second. Anyway, this course is more about the theoretical foundation of the DFT. And here, one of my messages is that whenever you have difficulty to derive a general form of the answer, first start from 1, then 2, then generalize to many. This is too simple, but very, very important. Sometimes you are much frustrated by the general result, but actually those results appearing in the textbook and also in research papers, the authors derive by using this step, and they just do not put these small steps, but showing giant leap. So we may be often frustrated, but don't be fooled by those general forms. Anyway, we are going to see that again. Let's review what we learned last time. So I've given you two different point of views or interpretations of the DFT. And this point of view is like this. So first thing is that our textbook and many old school DSP textbooks kind of show the difference between DTFT and DFT and also the similarities. So as you see here, as I summarized, you can find a very striking resemblance between the DTFT over discrete time signal or DFT over vector signal. The difference is that even though the notations look very similar, this x of n is the nth term of the sequence, infinite sequence. And here, x of n is the nth entry of a length capital N vector. Got it? And as you see here, they differ in the upper and lower limit of the summation, and also they differ in the radian frequency. However, still you see very much similarity appearing here. Of course, the synthesis equations are quite different because in order to recover original DT signal from your DTFT, since you have a function of omega which is a real number, even though this is periodic, you have uncountably infinite pairs of omega and the DTFT value. So when you synthesize, you need to integrate over the entire omega. Unlike the DTFT's synthesis equation, the DFT synthesis equation, or you may say that this is inverse DFT, has still finite terms. And you see, they are almost the same except the coefficient and the sign of the exponent. And whenever you have some similarity like this, you have so-called duality, which you can exploit to derive some results. And even though I didn't write it here, if you are a good-minded person, you can see the CTFT analysis and synthesis equation. They have exact duality because they are in the integral forms of the same infinite integration interval and function times complex exponential. Got it? So as CTFT has duality, DFT has duality, and we are going to exploit this one. By the way, DFT can be viewed in, so this is one of the way. So DFT can be kind of compared with the DTFT, but having some duality. That is one thing. The second one is kind of consisting of two things. One is that you view this one as what? Matrix vector multiplication. And here bifurcates two cases where we view this as a row of columns or a column of rows. And similarly, due to the duality, we have the IDFT, which happens to be 1 over n, and this DFT matrix Hermitian transposed X. So you see the striking resemblance. Got it? So actually, here goes something interesting we are going to see, and we've seen again and again. Even though DFT is for a transformation of a vector to another vector, it can be applied to discrete time signal processing because in many cases, not every time, but in many cases, we are handling the processing of time-limited discrete time signal. And what is interesting with discrete time-limited signal is that after proper shifting, we may put the support or duration of the signal to 0 to capital N minus 1 for some capital N. Then what we can do is that by viewing this as a vector X and writing this way, what do we have? We have something very interesting. Now let's see this thing as a row of columns. So we have V vectors and capital X 0 to capital X n minus 1. And these V vectors have e to the j 2 pi k divided by n times n. So actually, we can write x of n in this way. Here, this vector appeared just in your quiz, right? To limit the time. So it just keeps the zeros entry to up to capital N minus 1's entry and kind of nullify all the other terms. So this is very interesting. A discrete time signal can be written this way by using the DFT of this part, which is a vector. Got it? By viewing this way. So whenever you have DFT or IDFT, you must be able to view it as kind of what? the linear combination of columns, or sometimes projection of your right-sided input vector. In this case, we view it as a linear combination. So we have linearly combined complex exponential signals. So let's take a look at more on this, which I didn't do that. So let's consider from k equals 0. So whenever you have even infinite sum or finite sum, don't never be frustrated. The reason why I repeat this one, you know that. I was really frustrated whenever I saw infinite sum of even finite sum. But after I kind of had suffered a lot, I had a lesson. Hey, this is just a summation. This is a notation for sum of many terms. So let's see that. So k equals 0 means that you have a coefficient, capital X of 0. Now, what is this one? As a function of n, with k equals 0, what do you have? This one gives you here x0 times 1, x0 times 1, again and again up to here, right? So the 0th term for this sum gives you a constant that is time limited to 0 to capital N minus 1 times your 0th component of the DFT. Now, what about the first one? So you have capital X1, and now this one has k equals 1, which means that from 0 to N minus 1, your signal, complex signal, rotates the unit circle counterclockwise just a single time. So it's like somewhat, how do you say that? If this is the direction and you have the complex plane, the phase rotates that way. What about k equals 2? Then you have capital K x of 2, and then this one rotates twice until you reach here. And 3 times, 4 times, and eventually capital N minus 1 times. So you have kind of decomposed this part into what? Complex sinusoidal signals with different frequency. But this frequency is now discrete, fortunately, because the signal is time limited. You don't need infinite, uncountably infinite terms like this. You don't need that. So we are very fortunate in that we have a very powerful computer these days. Now it has a lot of memory, even though our textbook says that if the memory is, the length is too large, we have trouble. But these days, we rarely suffer from that trouble because of this electrical engineering left side building guys who developed a very fast DSP and very fast even general purpose CPUs and servers like that, programs. Got it? Anyway, so that is the key. So let me repeat again. Sometimes it's better to view your DFT as a matrix vector multiplication, which I emphasized a lot. However, still, sometimes it's better to just write down using this formula similar to the definition of DTFT. Okay? Because sometimes this way is much easier than matrix vector multiplication way. Got it? And I realized that while I was preparing for this part. So last time, we've seen some applications of DFT for discrete time signal processing. First one is that in order to prepare for that, we first define the circular downshift over vector. And in MATLAB, it's defined as circ shift. And here goes a vector, and here goes the amount of downshift. And let's consider circular downshift by 1. And of course, this kind of transformation is, since it is linear, we can find the circular downshift matrix like this. By the way, See that this is nothing but the identity matrix where last row is circular downshifted to become the first row. The problem is that this type of approach may give us other point of view, but sometimes it confuses us more. And that was the trouble of me in the last class meeting, murmured a lot. So even though this is okay perfectly, sometimes just using this approach is much better. Got it? So that is what it is written in the textbook. So let's consider this one. Suppose this y vector, this is y. Suppose y vector is a circular downshifted version of x vector. Now, the question is find the DFT of y vector in terms of the DFT of the x vector. And we know from the DTFT property, we guess that delay in time domain is a linear phase shift in the frequency domain. We immediately know that this should be a kind of linear phase shift. The problem is that is not easy to derive using matrix vector multiplication because linear phase shift, such as this one, is actually Hadamard producted with the DFT of the original vector x. And unfortunately, the Hadamard product is tricky. You need to introduce a diagonal matrix that has this as diagonal components. And this is sometimes very confusing. That's why last time I kind of murmured. And as our textbook shows, this is a better approach. Got it? Yeah. So in this case, this amount is just 1. So everything is 1. But if you have some k0, then it should be more downshifted, and you will have some, n0. You will have some n0 here. Got it? As you see here. And let's use n0. So let me repeat. Sometimes just using this definition is much easier. Sometimes using this approach is much easier to handle. You must be able to do both of them. Anyway, so circular downshift is a very important operation that can be done on a finite length vector. You need to keep that in mind. Now, here goes the first question. In your discrete time signal processing, DT signal processing, you've seen some case where you have two periodic signals with the same period, and you perform something called circular convolution. And circular convolution is very simple to define. It's similar to ordinary convolution. But the difference is that your parameter runs for a single period. So in ordinary convolution, you have lower limit negative infinity and upper limit positive infinity. But if you have a periodic signal with period capital N, two periodic signals, and circular convolve, it's similar to what? It's similar to do this one. you perform ordinary linear convolution, but after you time limit one of them. Got it? So as you've seen in the quiz, this trick using a rectangular window appears again and again to link the discrete time signal processing with kind of discrete signal processing, vector signal processing. Got it? Do you see that? Limiting one of the signal, actually periodic in this case, to a single period, and convolving these two signals with linear convolution is the same as the periodic convolution, right? Or circular convolution. And this circular convolution is very interesting in that here you perform the discrete time Fourier series, you find the discrete time Fourier series coefficients. What happens? The output is periodic because these two are periodic, and Fourier coefficient of this one is related to the product of Fourier coefficients of these two. That happens again in the DFT. And to prove that, here we started from a periodic signal, in this case x and y, and z is the output of the circular convolution. And of course, we can define x vector by taking the capital N of x, y vector, z vector in the similar way, and really do the circular downshift, blah, blah, blah. But it's much easier directly work on the z of n and the DFT of the z vector. So let's see. This z is now circular convolution, as we've seen. Just a second. Something's wrong. Okay. Just a second. Got it? Okay. So here, what we do is that we plug in this x by using the inverse DFT. Got it? And then what we usually do is that we change the order of the summations. And then by grouping these two, we can show that the z of n can be written this way. What does that mean? It's a periodic signal with this one as the Fourier coefficient. So what happens? The DFT of z vector is just the product of the DFTs. And in terms of these vectors of the DFTs, here comes the Hadamard product between x and y. But by directly using the vector matrix multiplication, it's complicated. You need to introduce a diagonal matrix. So let's just be satisfied here in this course. Now, here comes the important property of the DFT and IDFT. Since they are in the same form, we have very, very powerful duality. So even without deriving, we can claim something like this. Suppose you multiply Hadamard product, two vectors, to get z vector. Now, the question is, what is the DFT of this vector in terms of DFTs of these two vectors? And from the duality, here we have 1 over n, but anyway, by viewing this capital X of k as a periodic signal, and by viewing this capital Y of k as another periodic signal, and circular convolving these two and properly scaling, you can get the DFT of the Z vector due to duality, thanks to the duality. Got it? So that solves my stumble last time. Here goes the preview of today's class meeting, which is now 10 minutes left. Let me be quick. So this is the topic which I mentioned last time. So what we want to do in many discrete time signal processing is to convolve, linearly convolve two signals. So as I told you, we have x of n, a discrete time signal. We have h of n, a discrete time signal. We have y of n, which is defined as the linear convolution of these two signals. And as I told you, this linear convolution involves how many terms? Countably infinite terms in general. So it's very computationally costly. And even if x signal and h signal are time limited, still this may be very large. But as far as the signals are time limited, we've just seen that we can utilize DFT. And as I told you last time, ordinary vector matrix multiplication, which is related to the convolution in the time domain, has complexity big O of n squared. But the fast algorithm version of DFT usually has ordinary n log n. So even if n very large, we may save a lot of computational power by kind of performing DFT, doing some processing, performing inverse DFT. And our textbook approaches this problem this way. So as I just have reviewed, we've seen what? We've seen this thing. Suppose we have two vectors circularly convolved. Then we know that their DFTs are product of the DFTs. Can we utilize this one by performing linear convolution of two time-limited discrete time signals? Got it? And as you may have perceived in your brain, there is a direct method, like we take the some part of the x, some part of h, and directly perform DFTs and multiply and IDFT to have some signal back. While we do this, the trouble is that if the convolution was circular convolution, we are guaranteed to have the product of DFTs. But we are going to perform linear convolution. So the question is, when a circular convolution is not equal, we may say equivalent to linear convolution. And then when they are not equivalent, and if not, what happens? And as you easily guess, time domain aliasing occurs under certain conditions. What we are going to do is that we properly choose the FFT or DFT size or number of points to avoid time domain aliasing. And another one is that even though we have successfully avoided time domain aliasing, the FFT or DFT size could be still too large. Then what can we do? Of course, in general, we can't do anything, but sometimes this signal is much shorter, time limited, than that signal. In that case, we can devise clever methods to have smaller DFT size, but performing small size DFT more than once. Okay? So direct method is that n DFT probably 3 times. here overlap add and overlap save is kind of L, which is smaller than N, DFT, 3 times some many, but this could be much easier depending on your hardware complexity. And let's see. Let's just take a look at this figure first. So here, this is already emphasized last time. Suppose we have the extreme case where 2 signals to be linearly convolved are delta functions, exactly located at time 0. Then what is the output and what is the support duration of this signal? And you know that delta convolved delta equals delta. So let's say that the length of signal x as L, or P anyway, length of signal H as P, and what is the length of signal Y? As you see that, 1 plus 1 minus 1. So you have 1, right? So this holds not only for extreme case, but also for general case. As you see here, this is also an extreme case where we have a rectangular all one function, but the length is L, and here the length is P. And if you convolve these two linearly, then what happens? You have a signal that could be non-zero from 0 to L plus P minus 1. Got it? So remember this one. And whenever you have difficulty to remember, just remember this extreme case. Got it? Anyway, so what you do is, where this? Just a second. Where is the example? Just a second. Okay. Yeah. So let's focus on this example with a rectangular signal and ramp signal, increase and just drop. And we consider various choices of N. Here, N is to be used in DFT. Right? So what would be the safest way? The safest way is to choose this one as N. And as you see here, L plus P equals N plus 1. And what does that mean? This is greater than equal to 1. This is greater than equal to 1. So L is less than N. P is less than N. Right? So you can choose from 0 to N minus 1. And you can choose from here to the length N minus, so length N. So if you set this time as 0, then this time instant becomes N minus 1, right? So you have two length N vectors. Now you convolve these two, and what happens? Because this has only support of length L, and that has support of length P. When you circular convolve the periodically extended version of this one, what happens? No overlapping occurs between the other replicas. So we are safe. That is just the trick here. Got it? So when you convolve these two, you choose N larger than L, larger than P, and of course larger than L plus P minus 1, or equal to that. Got it? Otherwise, what happens? And that is shown here in the figure, like this. So here, time domain aliasing occurs so that we cannot get our desired linear convolution. Got it? So that is the idea. You just read the rest of the part. It's not that difficult. And here goes the key. So we have just shown that we have just seen that whenever we have two time-limited discrete time signals to be linearly convolved, by taking the chunk of the signal of length greater than the sum of these two signals length minus 1, and you kind of move that part to the frequency domain, this part to the frequency domain, and you Hadamard product and properly scale, and then perform inverse DFT and put that part in your output and nulling all the part of the output as 0, you are done. And this may be, as you see, as you may have already noticed, apply to this LTI filtering, then we are done, right? As far as the signals are time limited. And this time limited condition may look very strong, but as I told you, in practical point of view, every discrete time signal is time limited. Anyway, after proper choice of approximation. So here goes the trick. So if n is not too large, we can directly apply this idea. What if n is still large, but fortunately one of the signals, x or h, has length very short? That is the idea of this overlap add method and overlap save method contrasted to the direct method. Direct method is that we take large chunk. And here we see that, hey, still the one of the signal has support very short. Then here goes the trick. The idea is this one. The DFT and our LTI filtering is linear operation. So what we do is that we somehow rewrite our signal. In this case, it is assumed X has longer support. Got it? So X can be written as a sum of many parts. Of course, in this case, infinite, but probably some R. Got it? So what we do is that, so this is the signal X. We divide into smaller pieces and rewrite X as, let's say this is X0 and this is X1, n minus L, X2, n minus 2L, something like that. So as you see that we have R from 0 to some capital R minus 1. So this way, we somehow divide the signal into smaller pieces. And now what do we do? Since this is shorter than original signal, and we assume H has small support, what can we do? Now we can choose small size of DFT point. And we perform DFT, Hadamard product, inverse DFT. We can get back the output segment. And then at the output, we put this part, and then we put that part. So that becomes this add part. Got it? Then what is overlap and save method? Overlap and save method kind of divides these two overlapping parts and then does discard some part. And you can find that from many articles, but our handout only has this overlap add method, which can be exploited when one of the signal has much shorter duration. Got it? Anyway, it's time, so let me wrap up. See you in 2 weeks.